Hi guys, I will be going over the second paper of June 2023 series for OCR Physics A. Question number 1. Which of these units is a base unit? Well, the only base unit over here is the amps, so A is the answer. Question number 2, it says the accepted value of G is 9.81. In an experiment to verify the value of G, the students obtained this value. What is the percentage difference between the student's value and the accepted value of G? Well, that's one of the easiest questions they can ask you. So that's just basically the difference between the two over the original value, times it by 100, and you will obtain C as your answer. Question number 3. Which of these statements is or are true? Antiprotons are hadrons, so are subjected to strong nuclear and weak nuclear forces. So that is true because they interact through strong nuclear force, but they can decay through weak nuclear forces. Point 2, neutrons are subjected to the weak nuclear forces only. No, neutrons are hadrons as well, so they are the same strong and weak nuclear forces. And point 3, the weak nuclear force is the only force that causes a change of quark type. Yes, that is true as well. So that is going to be, well, C will be the answer here. Okay, question number 4. 200 watts heater is used for 90 minutes. The cost per kilowatt hour is 13 pence. How much did it cost to use the heater? Well, that's really easy. Again, energy is in kilowatt hour, so that's going to be 0.2 kilowatts times by 1.5 hours. So that will give you 0.3 kilowatt hour and just times it by 13 pence, which will give you A as the answer. Question number 5. We've got a diagram showing the path of a nucleus entering a magnetic field. So remember, nucleus contains protons, which is basically, those are the only ones that will affect the path, and protons follow the same path as the current does. So it says, in which direction does the force on the nucleus act as it enters the magnetic field? And the magnetic field is out of the plane of paper. So if we use Fleming's left-hand rule, we would end up getting A as the answer. You can try it yourself, but it's pretty straightforward. Remember the FBI rule, force acts by the thumb. B is the magnetic field, which acts through the first finger, and second finger is the current, and so it will, the force acting will be down the plane of paper, so A will be the answer. Question number 6. So it says technetium-99m is a metastable isotope used in medical diagnosis. Which ionizing radiation does it emit? This is one of the ones that you just need to know, and it is gamma radiation that it emits, so D will be the answer. Question number 7. The power dissipated across 1 kilo ohm resistor is 20 watts, and what is the potential difference across the resistor? So that's really easy again. P equals V squared over R, so if you just rearrange it, V will be the square root of 20 times 1,000, which will give us C as the answer. Okay, question number 8. The diagram shows the relative lengths and the diameters of the two copper wires labeled X and Y. What is the ratio of the resistivity of Y to X? Okay, very cheeky question. Resistivity depends only on the material mainly. So if the materials were different, then I would consider other things like diameter and length. However, they're both copper wires, so the ratio will remain the same. A will be my answer here, so be very careful there. Question number 9. The centers of a positron and a helium nucleus are separated by 2 millimeters. What is the electrostatic force between them? So again, relatively simple question, as long as you know a positron is a positive electron, okay, and therefore it will have that charge. And a helium nucleus contains 2 protons, so it will have a 2e charge, and they are separated by 2 millimeters, so we can just use F equals QQ over 4 pi epsilon naught r squared to get the answer, and when I plug in the numbers, I got D as my answer. Okay, question number 10. We've been given a column of air in a tube of length L, closed at one end, is forced to vibrate at its fundamental frequency. A standing wave is set up inside the tube. Okay, so fundamental frequency is the lowest frequency, and remember that if a tube is open at one end and closed at one end, it always starts off with an empty node at the open end and a node at the closed end. Okay, so something like this. And if the length of this tube is L, then clearly L is quarter of the wavelength. So therefore, over here, the number of nodes obviously is 1, and the wavelength is going to be 4 times L, so C is the answer. Question number 11. A ray of light is traveling through glass with refractive index of 1.51. The diagram not to scale shows the light incident on a glass-air interface. Which of these statements is or are true? So the first one is wavelength of light in glass is less than that of in air. Well, that is definitely true because the speed is slower in glass. Number 2, the refractive index of glass is 2 times that of air. That is definitely not true because refractive index of glass is 1.5 and that of air is 1. So that's out. And then finally, it says theta 2 is greater than 48 degrees. So we would need to check this out mathematically. Remember, first of all, that if theta 2 is 48 degrees, then angle of incidence, which is what we are interested in, will be 90 minus 48, so 42 degrees. Now, it's worth finding out whether it would refract with that angle. Okay, so I'm going to use Snell's law. So N1 sine I equals N2 sine R. And I'm finding out sine R over here, or R. And for the first medium, so this is glass is the first medium, okay, we have 1.51. Sine of I is sine of 42 degrees, divided by N2, which is 1. Okay, that is the refractive index of the second medium, which is the air. Now, if I plug that into my calculator, I would notice it gives me a syntax error, maths error, basically. And that's because of this high refractive index and sine 42. Okay, it mathematically doesn't quite work out the angle because it ends up giving us this number as greater than 1, and sine inverse of greater than any number greater than 1 doesn't work. So it will, in other ways, in other words, will give me an invalid result. So if, however, this angle theta 2 is greater than 48, let's say 49 or whatever, then this angle will reduce. Okay, this will become 41. So now if I just replace my angle by 41 degrees, well, that just about works. Okay, that will it's about 0.99 something, and that in the calculator works really well. So that means that increasing theta 2 would decrease the angle of incidence, and therefore the ray would be refracted through a certain angle. So number 3 is definitely correct. So my answer would be D. Question number 12. That the diagram shows a coil of wire rotating between 2 permanent magnets in a model generator. The coil is rotating clockwise about point P at a constant angular velocity. And which letter represents the output of the generator at the instant in the diagram? So at this time in the diagram, the coil is basically parallel to the magnetic field. So you can imagine that if you had lots of, obviously like a rectangular coil, Okay, and it was just sitting parallel, you know, like so. And obviously you have the rest of it. So when the coil is parallel to the magnetic field, it is cutting through the field lines. Okay, and you would see that if I was to draw it out like this. So if I had obviously n number of turns, you can see that the coil is going to cut through the magnetic field lines, right? So therefore, the the EMF generated will be maximum. The N phi will be minimum. This will be 0, but the EMF is going to be maximum. So in this case, it is letter A that is applicable to our graph and hence our answer. Question number 13. In Rutherford's scattering experiment, alpha particles are directed at a gold foil which has 79 protons and the distance of closest approach is 47 femtometers. What is the best estimate of the work done on an alpha particle as it moves from a distance of 53 femtometers to the point of closest approach? So if an alpha particle is coming in towards the gold, nucleus, it's coming from, it starts off at that distance and it approaches a distance of 47 femtometers. Now we know that work done is the force times distance moved, and we know that force is the electrostatic force over here of repulsion, and that's due to the two electrons in the two protons, my bad, in the alpha particle's nucleus. Alpha particle is a helium nucleus, and 79 protons in the gold nuclei. So that over 4 pi epsilon naught, and the difference between the distance, which will be 6 times 10 to the minus 15 squared, and times by obviously the distance moved, which is also 6 times 10 to the minus 15 meters. So in other words, it just basically cancels out one of the denominators and ends up giving you a rough answer of D. Okay, so that gives me the answer there. Let's move on to question number 14. So a step-down transformer has an input potential difference of 200 volts. There are 250 turns on the primary coil and 50 turns on the secondary coil. Okay, let's put that down. So that is VP. This is NP. We are given NS, and we are also given that the secondary coil is connected to 1 kilo ohm resistor. What is the current through the resistor? So I'm going to work out what is the voltage through the secondary coil first, and then work out the current thereafterwards. So VS is equal to VP times by NS over NP, and it ends up giving me 40. And then I know that current is going to be VS over R, which is going to give me 0.04 amps, so B will be the answer. Question number 15, it says, which statement is Faraday's law? A, which is the direction of the electric current induced by a changing magnetic field, is such that the magnetic field created by the induced current opposes the changes in the initial magnetic field. No, very subtle differences, but that's not Faraday's law. However, part B, well, it says the magnitude of the electrostatic force between 2 point charges is directly proportional. Well, that's not Faraday's law. That's Coulomb's law. And C, the the magnitude of induced EMF is proportional to the rate of change of magnetic flux linkage. Well, that is correct. So C will be the answer here. Okay, let's move on to section B now. Question number 16 says that we've been given a pattern obtained by in a Young double slit experiment, And the pattern is not to scale. 3 regions of the pattern are labeled as A, B, and D, and the central maximum is labeled C. Red light of wavelength 640 nanometers was used in the experiment. The distance between the centers of the 2 slits is given to us, and the distance between the screen and the slits is also given as 4 meters. So it says, name the physical processes that cause the features labeled A, D, and B and C in figure 16.1. So A and D are basically dark fringes. So that is going to be due to destructive interference. Okay. And with B and C, well, we have bright fringes, which is due to constructive interference. So that is that. Part B, the Young double slit experiment uses coherent waves. State what coherent means. Well, they're the waves with constant phase difference and same frequency. Part C says, explain how the part of the pattern labeled B is formed. So B is right here, which is, so we've got our central maximum, okay, which is at 0 phase difference. And you have 1 and 2, okay. So basically, when the phase difference is, you can explain this actually using 2 ways, either phase difference or path difference. Phase difference, whenever you have constructive interference, is always in even multiples of pi, such as 2 pi or 4 pi, etc., etc. And then in terms of the path difference, you basically have whole multiples of lambda. So I could either say that when the phase difference is 4 pi radians, or when the path difference is 2 lambda, the waves will arrive in phase and therefore form a constructive, or rather, a bright fringe. Okay. Part D, calculate the angle theta from the central maximum C to the maximum labeled B, as shown in figure 16.2. Okay, so we know, first of all, that n lambda is equal to d sine theta. So theta will be equal to sine inverse of n lambda. Now, n, as I said earlier, is 2, okay? And 2 times the wavelength, which is 640, times 10 to the minus 9 over the distance, the d, the value of d, which is the slit distance, and that is 10 to the minus 5. And that will give us 7.35 degrees, or I can just round it to 7.4 degrees. Okay, question number 17 here. We've been given a, it's about medical physics, so very theoretical concepts here. Ultrasound B scans can be used to image unborn babies. Explain what is meant by ultrasound. So these are the longitudinal waves with frequencies greater than 20 kilohertz, basically. Part B, it says 17.1 is labeled is a labeled photograph of an ultrasound examination of a patient, and explain how the transducer both produces and receives ultrasound waves, and explain the purpose of the gel. Okay, so it's a very nice 6 marker if you know your theory, basically. So a transducer contains piezoelectric crystals across an alternating potential difference. So when potential difference is applied, it causes it to vibrate at the frequency of the applied potential difference, of course. And this produces pulses of ultrasound waves. And as ultrasound pulse is reflected at the boundary of the tissue and returns to the transducer, the crystal will then vibrate, producing an alternating potential difference across the crystal. So at the boundary of different media, some of the waves are reflected and some are transmitted based on the acoustic impedances. I don't know whether I say this right, but yeah. And then and we know that the greater the difference between these impedances, the greater the reflection and the smaller the transmission. So there is basically a large difference in the Z value of air and skin. So ultrasound would be largely reflected at the skin. So therefore we use a coupling gel, and that's because it has a similar value of Z, i.e. acoustic impedance, to the skin. So most of the ultrasound will be transmitted through, basically. Okay, let's move on to the next part. We have figure 17.2, which shows a B scan of an unborn baby. Explain why no signal is received back from A. Well, because there's nothing to reflect from. Part II. Explain why a greater signal is received back from B than C. Well, that's because tissue at B is denser. It's skull, right? So it's denser. So Z value at B is greater than at C, which is softer tissue. So that's why you're going to have a greater signal back from B. Part D. Doppler ultrasound can be used to measure the speed of blood flow through blood vessels. The speed of ultrasound in blood is 1600 meters per second. A transducer emitting ultrasound of frequency of 10 million hertz is placed at 50 degrees to the blood vessel. The reflected ultrasound has a frequency of 9.9987 megahertz. Calculate the speed V of the blood flow. So we have a very nice formula for this. So V is equal to delta FC over 2F cos of theta. And delta F is basically the difference between the two frequencies. So 10 minus 9.9987 times 10 to the power of 6 times by the speed of light divided by 2 times the original frequency, so 10 to the 7 essentially hertz, times by cos of 50 degrees. So that will end up giving me 0.16 meters per second. Okay, question number 18. Figure 18 represents a tube open at both ends. Air inside the tube is forced to oscillate by a speaker and produces a standing wave. The length of the tube is 30 centimeters and the wave speed inside the tube is 340 meters per second. Okay, and we have to sketch the standing wave for the fundamental mode of vibration. So both the ends are open, so we're going to have antinodes, and it's fundamental, so it will hence look something like this. It will have one node, like so, and really bad at drawing these sketches. One second, I'll just get my dotted line up. So it will look something like this. Okay, right, let's move on to the next part. Calculate the frequency, F0, of the speaker that is producing the standing wave inside the tube. So F0 is equal to V over lambda, 340 divided by lambda. Now lambda over here, so L is lambda over 2. So therefore, lambda is 2 times 0.3, and that gives me 567 hertz. Part C, the frequency of the speaker is increased, and calculate the next frequency that would produce a standing wave in this tube. So F1 basically is going to be equal to 340 divided by now the value of lambda. Okay, given that the frequency has increased, okay, to the next level, the value of the wavelength is going to be the same as the length, because it would basically form a whole wave inside the tube. So that would be just 0.3 meters, and that would give you a value of 1.13 times 10 to the power of 3 hertz. Okay, Question number 19. The picture shows an electron diffraction pattern produced by graphite in a cathode ray tube. Describe an experiment that produces this pattern. Draw a labeled diagram of the apparatus to help you with this. So it's a 4 marker, so we really have to condense it. So I'm going to put a diagram right here. So let's just quickly go through it before we start writing. So as you guys know, a cathode ray tube has got a cathode which is hot and it basically emits electrons. And this case we have the anode, which is a graphite anode, and graphite is made up of carbon atoms, okay? And as the electrons pass through this anode, the electrons will diffract and they form this pattern on the screen. Okay, it's like fluorescent tube. However, it's a very, very basic experiment. The reason why the wavelength, or rather the electrons diffract, is because their wavelength, the de Broglie's wavelength, is similar to the gap between the atoms in graphite. Okay, so I'm going to say that the electrons are emitted from the hot cathode, which is thermionic emission, where they accelerate through a high potential difference towards a graphite anode. Then they are diffracted through graphite as a gap between the atoms is approximately the same as de Broglie's wavelength, which is that of the electrons. And electrons are deflected on the screen with the diffraction pattern, as stated. Part B. Explain why light and dark circles are shown in the picture are produced, stating what this evidence provides about the electron behavior. Well, this provides the wave nature of electrons, as the light circles are due to the constructive interference and the dark circles are due to the destructive interference of the electrons. Part C. A potential difference of 5 kilovolts is used to accelerate the electrons. Calculate the work done on the electrons. Easy peasy. W is equal to EV, 1.6 times 10 to the minus 19, times by 5,000 volts, which gives me 8 times 10 to the minus 19 joules of energy. Calculate de Broglie's wavelength of the accelerated electrons. Okay, so there is one equation which is given to you, and that is lambda equals h over p. However, because we are dealing with the electrons in terms of their momentum, we don't really have the velocity, right? So we need to do a little bit of manipulation for this formula. Now, I've done a whole video on this particular derivation, and I highly recommend that you check it out. I will hopefully remember to put a link at the end of the video for that. But I'll just still go through it anyway over here real quick. So we know that h over m times v is lambda, and we know that the work done is the kinetic energy is equal to half mv squared. Now, if I just make v the subject from here, I would get 2 ek over m, okay? And I would have to sub that into my equation here, and I would end up getting 2 ek over m, as in square root. And if I just tidy this up slightly, as in rationalize the denominator, I would end up getting 2 ek m, all square rooted, okay, which is very nice. So you can either remember this equation, or you should follow up the steps to figure out this formula. So we've got everything now. So all we got to do is plug in these values, and the kinetic energy is, of course, from part C, I, 8 times 10 to the minus 16. And m is known to us, of that of electrons, and voila, you will have your answer as 1.74 times 10 to the minus 11 meters. Okay, part I. Suggest a value for the spacing between the graphite atoms. Justify your answer. So it would be expected to be the same as lambda, as I've calculated, for the diffraction to occur. In question number 20, it says that in an experiment, a circuit is set up so that a capacitor with the resistor is in series, and it can be charged, and at some later time it can be discharged through the same resistor without changing the positions of the components, and this process can be repeated. So the supply has a potential difference of 6 volts DC, the capacitor has 1 microfarads of capacitance, and resistor is 10 kilo ohms. A voltmeter is used to measure the potential difference across the capacitor and draw a circuit diagram for this. So I've got one over here, so just adding that, and there we are. So I'll leave it there, quite straightforward. All you got to do is switch the positions of this switch right here and be ready for it to be discharged through the resistor. So the next part of the question is asking us to calculate the charge Q stored on the capacitor when it is fully charged. So that's really simple. Q is equal to C times V. Capacitance is 1 microfarad, so that's 10 to the power of minus 6 times by the 6 volts, and that gives me 6 times 10 to the minus 6 coulombs of charge. Use a calculation to explain why it is not possible to measure the variation of potential difference across the capacitor with the time using a stopwatch. So the time constant is basically equal to RC. That's something we know, that it takes the voltage or the charge to drop to 37% of its original amount. Now RC happens to be 10 to the power of 4 times by 10 to the minus 6, which is a very, very small number. So this is basically too short for any human to react to using a stopwatch. Hence, it's not ideal. Okay, part D. State how this experiment can be modified to measure the variation of the potential difference across the capacitor with time as capacitor charges. Well, we can use a data logger with a voltmeter. Next, it says the capacitor was completely charged and then discharged to 4.12 volts. Calculate the time required for the potential difference across the capacitor to reach 4.12 volts when discharging. So we know the equation for discharging is V equals V naught E to the power of minus D over RC. And if you want to work out the time, then we can just rearrange it and ln both sides, and it would look something like this. And then this value is going to be negative, and so we'll cancel out with the negative sign. And we know that RC is 10 to the minus 2, so we can work out T as minus 0.01 times ln of 4.12 over 6, which gives us 3.76 times 10 to the power of minus 3 seconds. Okay, next part. We have to calculate the average rate at which energy is lost by the capacitor as it discharges from 6 to 4.12 volts. So we know that the average rate of energy lost is essentially power, and so power is energy divided by time, and we know the time that it took for the capacitor to discharge from 6 to 4.12 volts was this much, and so we just have to think about the energy lost. So that will be half times C times delta V squared divided by the time, which is 3.76 times 10 to the minus 3. We are given the capacitance, and so that's 10 to the minus 6, and we know the change in voltage, which is 6 minus 4.12 squared, and put that all in the calculator, and you will get 2.53 times 10 to the minus 3 watts, or joules per second. Okay. We have the next question, number 21, which is about nuclear fission reactor. which is used in a nuclear power station. Complete the labels on the diagram. So this is really basic. We know that these are the fuel rods, and this is basically a moderator. So that's that moderator, and part B is a 6 marker. So it says describe how fission of nuclei is induced and controlled in the nuclear reactor. That's a nice question. Show how fission leads to the release of large amounts of energy. Okay, so we have to think about the energy released as delta mc squared. And we've been given a bunch of data. So let's start by talking about the first part, which is the fission of nuclei induction and the control of that. So we know that uranium-235 nucleus absorbs a slow-moving neutron, which causes uranium-236 to form, and that's unstable, and it basically fissions. It fissions to form barium-141, krypton-92, and that would release 3 neutrons because neutron has got a relative mass of 1. And of course it releases energy. So these neutrons released need to be slowed down, which is done by the moderator, and excess of them will be absorbed by the control rods for further chain reactions to occur in a controlled manner. Otherwise, we would end up getting uncontrolled fission, and it would lead to release of just crazy amount of energy, which could lead to an atomic bomb, basically. So that's the job of the control rods. The energy released, that's we know that it's given by delta mc squared, and delta m is just basically the difference in the mass of the products and the reactants. We're going to use the atomic mass units given in our data table, and basically we are given that krypton and barium are 140 and 91 and then we also know neutrons, which are 3 of them, must be multiplied by 3 for this reaction, and then take away the mass of the reactant, which is basically uranium-235, but also the neutron. Okay, so don't forget the neutron, because we are only given the mass of uranium-235 here, but it is uranium-236 that fissions. So we would end up getting 0.18604 atomic mass units, and we just have to times it by the relevant conversion, which is 1.661 times 10 to the minus 27 kilos per atomic mass units, which will give us the mass in kilos. And then we just have to multiply it by the speed of light squared, and we end up getting roughly about 2.78 times 10 to the minus 11 joules, which is, again, if you convert it into EV or mega EV, it is 174 MeV, which is per reaction. Okay, part C, we are given that the energy released for the fusion of 1 kilo of hydrogen is more than 7 times the energy released by the fission of 1 kilo of uranium. Compare the practicalities of using nuclear fusion of hydrogen with using nuclear fission of uranium to meet our energy needs. So the first thing that comes to your mind is uranium-235 is finite, but hydrogen isn't. So we have abundance, and therefore the amount of energy, we don't have to worry about how long we can use it for. Then the second thing is fission of uranium-235 produces radioactive waste, and storage, of course, is a serious safety issue, but fusion of hydrogen will, it doesn't produce any radioactive waste. And thirdly, I guess we can say that fission is spontaneous and it's basically self-sustaining once it starts, but for fusion, you need very high temperature and pressure to start and basically carry that throughout the process. So those will be my key points here. Okay, let's move on to question number 22. The radiographers commonly use molecules containing fluorine F18 as tracers in positron emission tomography, and fluorine has a proton number of 9 and it decays into oxygen by a beta positive decay. Write down an equation for this. So we know F18 with 9 decays into oxygen, and if it is a beta positive decay, we know it will release a electron neutrino, and oxygen will be 8 and the atomic mass will be 18. So for beta part B, the beta positive travels only a short distance in the patient before it meets an electron and is annihilated. Calculate the wavelength lambda of gamma photons produced. So we know that E equals hc over lambda, and we also know that the rest mass energy of the electron is mc squared, and so these two are equal to each other as energy is conserved, and we can say that since hc over lambda is mc squared, we can cancel out the c, and then lambda may become h over m times c. So we've been given everything, and we can use all the constants and get our answer as 2.4 times 10 to the minus 12 meters. Part C. X-rays and gamma rays are produced by different physical processes. Briefly describe both processes. So X-rays are produced when the electrons de-excite, basically. And gamma rays are produced in unstable isotopes when the nuclei decay. Okay. Part D is F18 has half-life of 109.7 minutes. Explain the advantage that this has for the patient, but a disadvantage this has for the radiographers. So the advantage is that the exposure of the ionizing radiation to the patient is low due to its short half-life. And disadvantage to the radiographers is that they only get a small, short window of time to scan the patient. Okay, let's move on to question number 23. It says, as the light passes through a substance, its intensity decreases exponentially with distance. And we've been given a bunch of terms which we already know. And some students are studying the absorption of visible light by red jelly. Interesting, okay. They set up the experiment below, and we have a filament bulb, jelly of different thickness, and the light meter. It says that the power to the bulb is kept constant. The distance between the bulb and the light meter is also kept constant. Blocks of jelly with different thickness are used, and they measure the intensity of the light using a light meter. Okay, and we have been given a bunch of data points over here, and we need to work out the first two columns. So this is basically ln of the light intensity, so that's just really simple. Using a calculator, we get 4.80 and 3.84 to 2 decimal places. And then we have to plot the results from the table on the graph. 3 points have already been plotted for us. So just going to go ahead and plot out. So those are my points, and I'm going to probably draw a line of best fit. Yep, draw a line of best fit. So, okay, so show how the equation for the exponential absorption of light can give a straight line graph with a negative gradient. Okay, so we know that I is equal to I naught E minus mu x. Now if we take, because this is a ln graph, so we should ln both sides, and as we know that ln I equals ln I naught minus mu x, okay, will be the equation using just the log rules, okay, and with this, if we compare it to the equation of the straight line, which is y equals, mx plus c, okay, we can safely say that m, which is a gradient, is negative mu. So that's just the it shows that it has a negative gradient. Okay, and then for part II, we have to use a graph to determine the intensity of the light I0 before it enters the jelly. So for that, we know that that's the y-intercept, ln I0 is the y-intercept. And if we just do that right here, that number is 5.8. So ln I0 is 5.8. And therefore I0 is e to the 5.8, which gives me 330 watts per meter squared. For the next part, we have to use a graph to determine the constant of proportionality mu in units of per millimeters. Okay, so let's go up and work out the gradient of the line, and that is going to be our change in y will be 5.8 minus 0.9, and the change in x will be just 5. And so that gives me, it'll be a negative, so a negative right here, so it gives me minus 0.98. And yeah, so that will be the value of the gradient, so we know that that'll be 0.98 per millimeter. Okay. Part C, we have the students decide to make their own light meter using this circuit. The value of R1 is 5 kilo ohms, and the value of R2 is 100 ohms when 1 millimeter jelly is used, and 8 kilo ohms when 5 millimeters jelly was used. Calculate the output voltage range obtained in this experiment. Okay, so we have to work out what would be the output at 100, using 100 ohms, okay, and using 8 kilo ohms. That's a massive difference there. So we know the potential divider equation, which is V out is R2 over R1 plus R2 times by V in. I think this is a very, very nice question, very easy question. So we know that at 100, we would have 100 over, this is obviously 5,000 ohms, and so 5100 times by the input voltage, which is 5, and that gives me 0.098 volts. Similarly, at 8,000 ohms, we would have 8,000 over 13,000 times by 5, and that gives me 3.077 volts. And so the range of the voltage will be the difference between the two, and that will give me 2.979, or you can round this to one significant figure. I would just do it to one significant figure, so 3 volts. Okay. Part II, we have to describe 2 ways the output voltage range could be increased. Well, you could increase the input voltage, okay, or you could also decrease the resistance of the fixed resistor R1. Okay, so that's that. And finally, we have to explain how the circuit responds to a change in light intensity. Well, as the light intensity, let's say, increases, then the value of R2, which is the LDR, will decrease. So the potential difference would decrease and the current, therefore, would increase. Okay, that is it for now. I hope you found this paper useful. To be honest, it wasn't that hard of a paper compared to some of the ones in the past. So I'll see you guys next time with paper 3.